In the last video, I talked about how you can start from Bohr's condition about the radius of the orbit at the momentum times radius of the orbit is equal to a whole number times Planck's constant over 2 pi, which we know after the Broglie proposed this relation about that relates momentum to the wavelength of an electron. We know that this relation comes from requiring that there's a whole number of wavelengths around the orbits. So in the last lecture, I talked about how we can use this relation together with the relation for the centripetal force, how we can use this to find the radii of orbits that are allowed, because the n here has to be whole numbers. So going through the steps, I worked out a few values for n equals to 1, 2, and 3 for the allowed velocities, and these are the values that I got, and the allowed radii of the first 3 orbits. These are what I got. Now, I've also talked about how one of the main aim of this model of Bohr's was to try and explain and calculate the line spectrum of hydrogen, and that the idea of Bohr was that the line spectrum, the lines in the hydrogen spectrum, comes from the electron falling from a higher to a lower orbit and then giving out the energy that it lost as a photon of light. So in order to do this, we must therefore be able to we must first know the energy of each orbit, of each of these possible radius. Right. So, and therefore we need to find the energy of each orbit, and we understand from previous videos that the energy of the electron in this orbit consists of its kinetic energy and its potential energy under this attractive force. So in order to find the energy of the orbit, it means that I have to total up this kinetic and potential energy. So let me start by doing that. Clear this out first. Okay. The kinetic energy, let me just write down total energy is equal to the kinetic energy, which is half mv squared. M here is the mass of the electron, plus the potential energy. Now the potential energy will be the electric potential energy between the electron and the proton, and since the charges are minus E and E, opposite charges, it would be an attractive potential, and therefore this electric potential would be negative. And we know from what we have learned in electric field and electric potential that the formula comes from Coulomb's law. So that's E squared over 4 pi epsilon naught R. That's the electric potential of the electron. So this gives us the total energy. Okay, this one is negative, that's why we have a minus sign there. Right. And once we have this, we can now calculate the energy, the total energy for each orbit, because m here we know the mass of the electron. That will be me. Okay, mass of the electron is, I'll write it down here. Me is equal to 9.1 times 10 to the minus 31 kilogram. E and epsilon naught. E is 1.6, 10 to the minus 19 coulomb, and epsilon naught is 8.85 times 10 to the minus 12 in SI units. So these are actually good to memorize, although it would always be given in exams. Makes calculations quite fast. Okay, so we know these constants, and we also know for each orbit, like for the n equal to 1 orbit, smallest orbit, we know the values of v and r, which we need here and here. So therefore we have all these values for each n. Okay. So therefore let me then write down the values of E that we would get. Okay. Possible values of n, possible values of corresponding values of E. So when n is equal to 1, we can substitute these values, all these, into here. Okay, and using our calculator, we should find, or I have found, minus 2.180. And there's also times minus 18 joule. I'll write this up here, so it saves me writing for the next few. Okay, and just repeating this for n is equal to 2, where we have another set of values for v and r, but the same for the physical constants. You can substitute into this equation again, and then use our calculator to calculate the value of the total energy for the next orbit, the n equals to 2 orbits. And the answer is minus 0.5450. So just repeat that for n equals to 3. Okay, right, that gives minus 0.2402. Okay, now for what is going to come next, as in maybe later or the next video, I would need the values for another 3 orbits. Okay, I will need 3 more values in order to calculate the line spectrum of hydrogen. Okay, so let me write down all the numbers that I have found. Okay, so that would be minus 0.136 2 minus 0.08719 and minus 0.06055. Okay, and it is often useful to have these energies in eV. And we get that by dividing each of these numbers by electronic charge. So that would give us the energy in units of eV. Because these numbers are very small, whereas if it is in eV, which is itself a very small unit of energy, then the numbers would look simpler. Like for example, if I do it for this, if I divide this by E, that means by this, by that very small number, we would get minus 13.6. Okay, so that looks like a simpler number than, minus 2 point something times 10 to the minus 18, which is quite a lot of things to write. So minus 13.6, and that actually is a good number to remember. It's kind of quite famous for the hydrogen atom. Is the energy of the lowest orbits, or the most stable orbits, or the ground states, as it is often described. And I'm just going to write down a couple more. So the next one, if you divide that by E, meaning that and that, would be minus 3.04. If you do it for that, you get minus 1.51 and so on. Okay, so hopefully this will make us more familiar with what's going on in the hydrogen atom and how the energies of the orbits can only take definite values, discrete values. Alright, they can only occur in steps, not regular steps, as in from here to here and from here to here. The energy steps are different, but it would be still in steps because there's no energy possible in between two of these values. At least at the moment, that is what Bohr would have calculated. In order to be sure that this is really what happens, we have to check, right, whether using these numbers, whether we can actually calculate the correct line spectrum for hydrogen. Clear this up. So what is the plan now? Now that we have these energies, let's think about how we can use this. Right, these energies, correspond to the different orbits of the hydrogen atom. So if I, for example, draw some circles to represent each of these orbits, I might have n equals to 1, the smallest orbit because it has the smallest allowed radius. 2 might be the next size up, and then 3 the next one, 4 the next one, and so on and so on. So we can have lots and lots of orbits. In fact, we can have an infinite number, and each of these orbits has a corresponding energy. Now I'm going to call this energy should I call this? Okay, I'll call this E1. E1 because n is 1. I'll call this E2. I'll call this E3 and so on. Okay, so the lowest orbit energy is therefore E1, and the next one up is E2, next one up is E3. Excuse me. Okay, and so on. Alright, and we have the numbers here. Now, there is, rather than drawing circles all the time to represent this picture and these energies, a common way to show pictorially, to show in a picture these different energies is to draw what is called an energy level diagram. So an energy level diagram, let's see what that is. It's basically a graph, or kind of a graph, where, let's see, maybe just an axis, the energy axis. Okay, let's say that this energy is in EV, then and let's say that's 0. That's the 0 energy. Then the idea is that on this line we would mark out the energy for each orbit. So the lowest energy is minus 13.6 eV. So I would mark out minus 13.6, and next one up is minus 3.04. Maybe somewhere there, 3.04. Next one is up is minus 1.51. And so on. Right, and if I then draw a line, a horizontal line at each value of the energy along this axis, we can call this an energy level. Okay, so an energy level just means a certain energy where the electron can be at. So this would be the next level up. So n equals that's the first level, where n is equal to 1, n equals to 2, n equals to 3, and so on. And you notice that the energy values get closer and closer. Okay, and what you see here is that the magnitude gets smaller and smaller, but it remains negative. And in fact, if you keep going all the way to infinity, this would tend to 0. It would never become positive. Now the reason is because I think I'll show this in the next video, why this is the case. I'll show this in the next video. Maybe not immediately. Okay, but anyway, the reason why it goes to 0 at infinity is because for orbits that are further and further away, this attractive potential, it is over r. So r gets bigger and bigger, so this gets smaller and smaller, and the kinetic energy must always be less than the potential energy. Otherwise, the electron would escape. So therefore, the total energy must always be negative, right? Otherwise the electron would just escape. So because of that, as it gets smaller and smaller, okay, as the attractive potential gets smaller and smaller for larger and larger orbit, which gets further and further away from the center, so the kinetic energy must get even smaller than the magnitude of the potential energy. So that's why this magnitude gets smaller and smaller, and it will tend towards zero, but it will never get positive. So this means that the energy level diagram will look like this. Now, it will never go beyond zero, so we can draw a line there, or it won't go high up. But there would be an infinite number of possible values. So, remember that the n here means the number of wavelengths around it. So as long as there's a whole number of wavelengths, you can make it as big as you like. So what we have is an infinite number of lines in between. So you can imagine that the spacing just gets closer and closer and closer and closer and closer, and you get an infinite number of lines, all right, on the way up to zero. Okay. But for our purpose, we don't have to worry about all these infinite number of lines. We are just interested in using a few of these lines to see if we can calculate the line spectrum for hydrogen, which is what we hope to do. If we recall the line spectrum for hydrogen, sort of looks like this, with a red line, light blue line, blue line, and darker blue line. So we know the actual values of this, and in the next video I shall explain how those actual values how we can use this to calculate the values of these wavelengths.